See, definition is how close a measurement is to the true or correct value, like hitting the bullseye on a target. For example, a thermometer reads 98.6 degree Fahrenheit and the actual temperature is 98.6. So this is accurate. Now, what is this precision? It shows how consistent or repeatable the measurements are, regardless of how close they are to the true value, like hitting the same spot repeatedly even if it is not the bullseye. You weigh a patient 3 times and get 70, and next time 70.1, next time 70.1 again. So it's precise even if it's not correct, but it's precise. Validity definition is whether a test actually measures what it claims to measure. A valid test gives meaningful, relevant, true results. For example, if a depression questionnaire actually measures depression, it's valid. This selection bias. Selection bias occurs when the sample is not representative of the target population due to systematic error in how participants were selected or remain in the study. For example, you are studying the wrong people or not enough of the right people. But how to deal with selection bias? Dealing with selection bias at the study design stage. This is the most effective stage to prevent it, and this is the most effective stage. And strategies are random sampling, randomization, blinding of recruiters, and stratified sampling. Another is at data collection stage. This is where implementation matters, and strategies used are: you ensure complete follow-up, you train data collectors, you standardized recruitment, you track and report dropouts. So in a prospective or cohort studies, if sicker patients drop out and they are not followed, you overestimate survival. That is, there is this selection bias. So this prevent selection bias at design stage, and you control it at data collection, and you adjust it at analysis. But it's to be best avoided early. So at different stages, different goals are there and different methods are there. At for example, design stage, you prevent bias by doing random sampling, by doing stratification, by doing randomization. And at data collection, you limit bias by doing standardized recruitment and complete follow-up, because obviously patients who improved stopped coming, so that created this selection bias. And at analysis stage, there is adjustment and estimate impact, and tools to deal with selection bias are weighing, regression, this imputation, and this sensitivity analysis. So here this sensitivity analysis is you adjust for variables related to selection probability, and also you assess how results might change under different assumptions. That is sensitivity analysis. But dealing with selection bias at the analysis stage is you can do various you apply various methods. For example, propensity score matching, multivariate regression, sensitivity analysis, and imputation for missing data. For example, you estimate values for missing participants to reduce this attrition effect. You see, there are two things. One is attrition. Attrition is loss of participants after the study begins, but another is attrition bias. So that is when this loss is systematic and not random. That actually distorts the results. So simple definition of attrition bias is it's a type of selection bias that occurs when the characteristics of the participants who drop out differ systematically from those who remain. So when the key concept behind this is when people drop out, your sample is no longer representative of the original population, and if dropouts differ in exposure, outcome, or prognosis, your results are skewed. Clinical example we can give, for example, a cancer drug on effect of cancer drug on 5-year survival of a patient. We started with 100 patients, 25 drop out after 1 year because of, for example, severe side effects. Then you analyze only the 75 remaining who tolerated the drug better. So you overestimate survival benefit because sicker patients were lost. This is attrition bias and is a form of selection bias. So attrition bias is equal to when only the survivors speak. You end up hearing only from those who made it to the end, not the full story. So what can be the consequences? You overestimate or underestimate treatment effect, and you get underpowered results because there is less data, and it has got invalid generalization. For example, if we do RCT of a weight loss drug, you make two groups. For example, in one group you gave drug and in other group you gave placebo, and you started with 100 patients here and here, but dropped out patients number was 30 due to, for instance, nausea, but here dropped were 5. So final sample here was 70 and here it was 95, and average weight loss here was 10 kg, here it was minus 4 kg. But you conclude drug is effective, but those who dropped out were likely not losing weight. It inflates treatment effect. So what are the solutions at data collection stage for treatment of selection bias? One is retention strategies. So you reduce dropout by doing this follow-up and doing frequent reminders, and you track reasons for dropout. For example, that will helps assess potential bias, and you follow standardized protocols. That is what it does. It gives equal effort to retain all groups. So solution at analysis stages, intention to treat method. How it helps us, it includes all participants in analysis regardless of dropout, and you do multiple imputations. It estimates missing outcomes. And sensitivity analysis, it tests if results change under different dropout scenarios. And observation, last observation carried forward, it uses last available data point. So when iteration is related to outcome or treatment, it becomes bias. When it is random, it's just missing data. Always remember this. Another consequence with this attrition bias, because we know this is a systematic bias but not a random bias. So you are systematically excluding those more likely to have poor outcomes. That's why it overestimates safety and efficacy, because those who dropped out, they probably had poor outcomes. So some say in attrition bias, you are not just losing people, you are losing a type of person. It's a systematic one, because the loss is patterned, not accidental. You see, not all attrition is bias. If dropout is completely unrelated to exposure or outcome, this is just random missing data, not bias. But if dropout correlates with disease severity, adverse effects, socioeconomic status, response to treatment, it becomes systematic bias. You see, we can contrast with this random missingness. For instance, if a patient who received the drug became sick and he dropped out because of that, then it becomes a bias because it's associated with disease severity or adverse effect or the socioeconomic status response to treatment. But if some patient missed visits due to bad weather, so this is random. This is not related to outcome or exposure. So this is not a bias.